All right, QM everybody. As always, quick disclaimer, the discussion today is not a solicitation for investment and is not financial advice. The Quill and Wrapped Quill tokens that will be discussed in the broadcast are utility tokens, and Quilibrium Inc. does not endorse or encourage in speculation on the utility token of the network. With that aside, as always, we talk about what the mission of Quilibrium is. It is to secure every bit of traffic on the internet, whether it's on the Quilibrium protocol itself, in service of other protocols, or in service of the broader web. So today is going to be a little bit back into the way we used to do things, where the Sunday night streams are more dev-centric and other events are brought up in a different stream. So if you're here looking for like large updates and news, we're not going to be talking about much of that. I will go ahead and cover a few things real quick, but there's actually going to be another stream later this week where we'll dive into some of the more fun stuff. This is going to be very dev-oriented. I will forewarn you, I am completely flying blind right now. Like literally, Streamlabs is just showing me a big white pane on the preview, so I have no idea if any of this is working other than looking down at the Twitch stream on my phone. I don't know why it's doing this, but I guess that's just Streamlabs for you. So let me know if you can't hear me at all, because I have no idea. Okay, so a couple quick things. This last week, as a lot of you who have been following more closely know, we've been going through the process of ripping out and replacing the consensus engine with a different one that is a bit more battle tested so that we can overcome the issues we saw in the initial enrollment attempts. This will ultimately be culminating in the 2.105 release, but even before that release gets out, we'll start to see progress because it's still protocol compatible for at least some of the message types for 2.104. So if you don't upgrade, you're not going to be missing anything necessarily, but if you do upgrade, then you'll be ready to go when enrollment concludes. So we do recommend upgrading as soon as the update comes out, but it's just something to be aware of. Okay, cool. All right, thanks. Thanks for letting me know. Okay, so with that aside, obviously I know some folks are really excited about things like QNS, Quorum Mobile, all the Q associated services through Q Console, Q Storage, QKMS. That's coming up this week. I'm just letting you know now. Today we are focusing strictly on the consensus changes that are in place. So I'm going to go ahead and try to rearrange all this because I'm having a grand old time with Streamlabs right now. Okay, I assume that this is going to switch over. Cool, it did. Great. Oh, hey, you could even see for a brief second that Streamlabs was being stupid. Cool. Okay, so a couple quick things. If you've been following the 2.105 work in progress PR, obviously you can see quite a bit has happened. You'll also see a mention, if you were on the Node Runner Telegram, then you have heard some of the incredible input that's been coming from Black Swan. Major hat tip to you. It's been really helpful analysis and some interesting points that relate to all of the various ways in which node startup can happen that doesn't necessarily show up in testing or show up in a perfect environment where things are set up exactly a certain way where it's more predictable. So again, major shout out to Black Swan, and he closed this because of the work that has been going on in the 2.105 PR. And so I'm going to cover that. So to go ahead and dive into that, let's talk first about consensus. So a lot of the work this week has been largely in this package, the consensus package, which if you recall before was like 3 files, and now it's a much more substantial package, and it covers the hardened HotStuff style consensus. Now, we described the difference between our old consensus model, the state machine, strict linear order of events based consensus engine versus HotStuff in the last one. If you remember this diagram, then you're good to go on catching up with that. But the general principle is that things are broken down into a lot more distinct pieces, and that helps us more adequately, one, test the variant behaviors that can happen in the system, and also helps us more accurately model what the actual consensus scenario should behave like. So I'm going to walk through the primary entry point. So if you want a good example on what that actually ends up looking like in terms of an implementation, obviously when the PR is done, you'll see it plugged in directly into the node itself. But just at the pure integration level, where the only thing we're really mocking are the things that relate to external inputs, like the signing or production of frames. Essentially what we've done is we've taken a existing HotStuff implementation and we have basically genericized it so that it's not specific to that particular implementation. The implementation we adopted from was from the project flow, which is, they took the HotStuff implementation from Aptos, which was previously part of DM, the whole move-oriented series of protocols. And really, like their focus, like they had it pretty generic, but there were a few things that were like focused around block production in their specific way. And so we've completely abstracted that out, and now it's genericized. So you can plug in whatever state or vote types you're dealing with, or whatever the peer types are, or anything like that. And so what I'm going to walk through, and this is what a good portion of this prior week has been focused around, is these integration tests. And in particular, you can see the construction of the consensus instance in this integration test in the integration/instance_test.go file. The idea of this constructor, as I said, is to only plug in the things that are external dependencies otherwise, as mocks. Otherwise, it's the actual consensus code. And so what that results in is things like, for example, the committees, which is the coordination of members of the actual consensus set. The leader provider, which is whatever is dictating the ordering of leaders. And in our case, we have two different styles. We have the global style for leader order, and then we have the shard-specific leader orders. And so having that as a pluggable component is really important to us, because normally in a lot of chains where they just have like one singular block as a unit that they're iterating on top of, there's only one set of leaders. There's not many parallel tracks of blocks, in their case, frames in our case, being produced. And so that's why that's a pluggable component for us. Consensus store is just two very simple states that it's managing. One is around liveness, which is an important property of a HotStuff-based consensus engine, and then the other is the actual consensus state itself. Then we have a dedicated signer mock, which is, again, anything that's cryptography oriented, like BLS aggregation or verification, or the structuring of votes, all that plugged in. And so from that, we have all of the mock implementations for that, and it's really just a trivial implementation that gives us, a few pieces of info, like identities by rank has a different order in a normal, queue-based model, because the identity ordering is going to always be catering towards the output of what effectively is a verifiable randomness function in the form of the VDF that is processed on top of the frame. But in this case, we're just going to round robin it, so it's a little bit simpler. And you can see how that plays out with leader for rank. It's very basic round robining. And there's obviously no alternating memberships either. And then we also have our weight basis. Every single participant in this test model is using the same weight. It's 1,000, and then we give it a 2/3 ranking by, like 2/3 BFT consensus, by just simply taking the participant count, multiplying it by 2,000, dividing by 3 to get the 2/3, and obviously in the quantity of thousands. And then we have all the other pieces that are plugged in for voting, creating timeout certificates and timeout states, creating the certified states via creating the quorum certificates, and then the verification, which is just very, very simple. We just say, yes, they're valid. So not what you'd need in a proper instance, but for the sake of the test, it's pretty simple. And so the purpose of this is to basically have a few different things that we're running through. So the first is a basic like single instance-based scenario where we're just having it run through the series of what we call ranks. A lot of HotStuff implementations will call these views. And that's just literally the linear sequencing of consensus rounds. Rounds are separated from frames in our case, because in the HotStuff model, the way that they maintain consensus in the ranking order is based on whether it's a quorum certificate or a timeout certificate. As I was talking about in the last session, either of those can lead to the next rank. But that doesn't necessarily mean a new frame has been produced. Only a quorum certificate would be that. So that's why we have that separated out. And then there's obviously like a 3-instance model, a 7-instance model, and you can just keep incrementing those. But one of the things that we modeled in the 7-instance above case is models that are or instances that are misbehaving. So we have a bunch of levers that let us control whether outgoing votes are dropped or incoming proposals are dropped, or all the various things that it's going to communicate normally over PubSub, whether it's going to just either drop them or misbehave or whatever. And so with these conditions, we have a very simple scenario, which is, kind of what we were seeing with the prod scenario for 2104 and before, which was, one node was starting late or was slower or wasn't even an active member of the set. And previously we tried to model this, but we didn't really have as comprehensive of a way of capturing all the unique behaviors of how that was actually playing out in production. And so this serves as a really good way for us to actually vet those behaviors in advance and ensure that it does succeed in going through this. And very similarly, we also have the liveness considerations of these nodes that are participating in consensus that we have to care about, which is say that 2 nodes are effectively not participating correctly. Either they're unhealthy, misbehaving, whatever, and we have the case where basically you can treat it as if all traffic had just dropped going to them. But for some reason, it's still able to publish some things. And so in this scenario, we're essentially modeling 5 healthy scenarios, 2 that are timing out. And because it's BFT consensus, we should still progress even if there's timeouts. And so the expected pattern would be rank 0, good, rank 1, good, rank 2, 3, good. And then we get to rank 4, which is the 5th node. And the 5th node is an unhealthy replica, and then it fails because it isn't able to actually produce any proposals or votes. And so by consequence, the other nodes should proceed to reach a timeout condition where it advances to rank 5, and then from there times out again because the next instance is also unhealthy, then rank 6, and now we're back to a healthy instance, and so it's able to progress. And so these are the types of scenarios we modeled to basically cover all the different conditions that we were running into effectively in the mainnet environment. And so through all this, we have gotten to the point now where we do actually have all of those tests behaving correctly. We have a couple of other ones that get into a bit more nitty-gritty things. This last one here, the async cluster startup, very similarly behaves. What happens in a production environment where people are upgrading at different times, and you get this kind of rolling progression of nodes that are coming online. And so this simulates that in the worst possible way, where each of them is actually failing to propose their round's vote, and then they effectively come online. And that's actually really good for us, because if we can get through that scenario, then we know that our consensus model will be able to handle what we've been seeing in production. And so that's the gist of it. And that's actually played out quite nicely. So let me go here to this. I'm gonna make this verbose at a count of 1, and then we're gonna actually run. First, I'm gonna walk you through the first one, which is just the simple single instance happy path model. Okay, and so you can see bam, it just blasted through that no problem. And it's because we have, in these instances, we have the configured parameters of the consensus model. It's 100 millisecond frame production or proposal and timeout production, so it's a lot faster. And so we're able to get through it. It iterates through every single scenario and proceeds to generate proposals, builds on top of the proposals, goes to the next one, and so on, all the way until it reaches whatever the terminal condition is, which in this case we set to 10. And then once that 10th quorum certificate has been certified, it bails and passes. And so 3 instance, very similar behavior. The logs for this get pretty messy because now you have a bunch of different instances that are weaving in through each other, and you can see like through the self attribute. They're obviously like the same instance names between these two, but this one's a different instance. And you can see how on one it gets the proposal from the compliance engine, and the other one is still collecting votes until it has actually processed that. Then that comes through and becomes a qualifying certified state for that particular instance, and so on until it reaches consensus on each and every round. So here's where things were starting to get a little bit hairy for us, was trying to get through the process of getting timeouts to succeed. Because when you're going from something that is, deeply ingrained to another protocol in all their specific types, you run into the scenario that like it's going to start having leaky abstractions no matter how hard they try in terms of what those requisite consensus types are. And so, our working around that it produces a bit of an engineering challenge. And so what we were having happen was we're getting to the point where it was successfully reaching, like I said, it'd get to rank 4. And then once we got to rank 4, it would essentially fail out. I forget how much it logs before it actually has completed a state iteration. Let's see. Did we already? Oh, yeah. Okay, so here we go. So we're at rank 3, and the failing node, we should see a proposal somewhere around here. Yeah, here we go. Okay, so rank change, starting new rank now, and on, oh, wait, nope, this isn't the one, sorry. There we go. Okay, so then we reach the point where it's timing out, and from there we start to see the actual votes around this congregate around confirming that the state had actually successfully timed out, and then it proceeds to bump to the next round. And it will continue to do that until it reaches a healthy node, and then starts all over again, iterating through a bunch of states until it times out yet again. So that was all good. We got to the 7 instance portion, and then we got into the really tricky bit, which was like more specific conditions that certain things weren't communicating at all. The timeout speed was even more concise, leading to more possibility for race conditions to pop up, and that led us to the 2 out of 7 more direct timeout modeling scenario. And of course, as you can see, it passes because we've now gotten past all those issues. But that was probably about a day and a half worth of strife just to get through. And then the last bit was the async cluster startup, and that is where we get into one of the more crucial bits. So like I was saying earlier, Black Swan had mentioned in the Telegram group that we have an issue with some of the components that start. So when we look at the node, for example, you can see also that some of these files have errors right now because it's still being wired in. But in the actual wiring up of the pieces of the protocol, we have this panic guard, and that's fine. Like a panic guard for Go wire is actually pretty normal. It's like the most common implementation pattern. Nothing wrong with that. That basically means if there's an unhandled error, fail. Okay. But the problem is that we actually had in the pub subset the behavior where the peer-to-peer initialization would sometimes actually fail out pretty damn hard. So we'd have things like, no data worker configuration found. Well, okay, that's a reasonable thing to panic about. But we also had conditions that related to establishing PubSub itself. And so let me get to, I think it popped out here. It might have popped out somewhere later, but basically it would get to the point where it tries to establish a listener on the configured interface for the network of whatever that process is, whether it was a master process for the node or it was a worker process. And if it hit that condition, it would panic out. And what's dangerous about that, and it was something that he pointed out, is that we have a very temperamental database using PebbleDB as our primary persistence layer. And if it's doing something like, for example, it starts up and it decides, hey, I'm going to start compacting now, and you have a panic that kills it halfway through, there's a real risk that you could actually just corrupt the database doing that. And so that led us to adopting a general lifecycle facade. Because what we had before, if you look at some of our implementations, we had usually a start method or some variant of a start method, or we'd have the traditional Golang pattern of start with context. And there were a lot of different things that we would have using that pattern. And that's fine, like having a start pattern is fine, but what we didn't actually have is something to check readiness state. So when you think about the life cycle of a component, you have to consider that you have essentially a, where did I put it? There we go. You essentially have three things you're concerned with. You have the ability to start it. You have to have something that will let you basically wait on to be ready. And then when it has been shut down for whatever reason, you have a channel to wait on for done. And so oftentimes what people will do is they'll do start and done, and they use done with a context, which is why it's the start with a context pattern. But what happens here is that if you have a lot of intricate stand-up details that you need to do, like for example, you start the consensus engine. And I don't mean like the consensus engine that I've just been talking about, but like the encapsulating layer, the global consensus engine or the app shard consensus engine. When you start that up, it checks to see if you have the initial frame, the genesis frame for that given responsibility. And if you don't, it needs to create that. Well, that takes time. Worse, it takes time that is unique to every single machine because there's a VDF involved. And so by consequence, we need to be able to wait for readiness, and we need to be able to wait for readiness in a way that we can do all this in concert. And before, we weren't really doing that. We were just kind of shoving all the responsibilities of things that we care about in like this very piecemeal order in the start method, instead of actually like having a marked place for when it is ready versus when it is not ready. And so that's what led to this interface. It's got a bunch of different scenarios to be concerned with, and most importantly, we have this method called run component, and then we have a supervisor that allows us to orchestrate many different components altogether. And essentially what this allows us to do is it lets us take it to an extra level such that not only can we check for readiness or doneness, but in the event like the peer-to-peer scenario where the peer-to-peer, like the PubSub engine is popping up and it doesn't have a it doesn't have something that it needs ready. So in the case Black Swan described, for example, it didn't have the network interface. Like the interface hasn't been enabled yet. Like if you're running Q as a service on your machine on Linux, depending on the service initialization order, you could run into the scenario where there's literally no network interface for it to even listen to. And so it'll fail out, panic, and die. Whereas instead, we can actually be more reactionary to it and handle it accordingly. And so we have this notion of an error handling behavior. So for example, in the scenario in which a component just needs to restart, like say that it had, like it just needed to wait for a network interface to come live. Great, okay. Then we return this as our error handler so it knows, okay, I just need to restart. And then it can keep reiterating that until it finally succeeds, and then it will reach a ready state. We also have the notion of it should just stop, which means that it and any components that depend on it should be stopped, but should not shut down the entire application. There's like tracers and things you could care about, but not enough to actually want to terminate the whole thing. Stop parents would mean that it propagates all the way upward and stops the entire chain of dependencies. Shutdown is a cross-cutting concern. It's like, hey, this is so bad and so broken of a situation that we need to shut down the node. And then there's also like the absolute like disaster scenario of should spin halt. And so the reason we have that is that, let's say, for example, we have a monitor for disk space that we added in the original 2.10 release that basically has three conditions. It will notify you if it's reached 70% disk capacity usage. It will warn you if it reaches 90%, and it will terminate if it reaches 95%. Some people like to play a little bit more dangerously. And so there is the scenario in which you could either like set all these values to like 100 and say just completely disregard that, I don't care. But if you do that, you can actually run into a really, really bad scenario where it will stop because it ran out of disk space, because like, PebbleDB itself has now panicked. And then from there, the entire system will completely stop, crash, and then if you have it on a service that reruns on failure, it'll just keep restarting. So you could potentially get yourself into the scenario where it's run out of disk space and you're now thrashing it so hard that you're corrupting your database and you won't be able to recover from that. And so the purpose of spin halt is in a scenario that's that kind of catastrophic, we shouldn't actually shut down. We should put ourselves into a state that's just spinning and halting with a log message saying, hey, you have reached a critical state. You need to resolve this first. You won't be able to just Control-C your way out of this. You need to issue a SIG term to the process and do not let it restart as a service. Which is a lot nicer than what Ethereum does, where if it has a catastrophic failure, it's just like, cool, okay, wipe the database, start all over. Don't know why they do that, but that's still what they do after all these years. Okay, so that's our component model. And like I said, we have a supervisor component as well, which allows us to create a topological graph of dependencies, and it will start things up in the requisite order, wait for readiness in the requisite order, and then shut down in the reverse order of dependencies so that everything shuts down quite nicely. That's really useful for us on some of our like more message-driven dependency services like vote processing and timeout processing, where it's got potentially an accumulation of messages that would build up on dead consumers because the consumers were shut down ahead of the actual broker for those messages. So that's just a really nice thing to have. And so that's basically what the majority of this work's gone into. And so all this monstrous amount of work that's been required to get this all up and running ultimately culminates in a very simple package. We just have a participant, which actually sets up the consensus loop, and all you got to do is plug in the relevant dependencies. So for you, as an implementer of consensus, whether you're building a if you're just building the queue node, of course you'll be using this with all the plugged in dependencies. Or if you're actually writing your own protocol, or you're writing a custom node to do things like the alt-fee basis app shards that I've talked about quite a bit now, this enables you to define the state that you're performing consensus over. So for example, if you're doing an alt shard like we're going to be doing with our bridge, where we're actually taking in like a Ethereum execution engine that's just processing blocks, we plug in those blocks as the state component. The vote will take as the beacon chain vote, so it's like the weighted voting of staked voters. The peer ID, that's not actually too relevant in this case. And the collected model would be like essentially mempool entries. You just plug in all of those components relative to the specific implementations that you need to piece together, and you get this really nice consensus engine that essentially brokers things out into the relevant components that you need to plug into in order to push all of that information upstream for your alt-fee basis app shard. And so pretty simple to do then. Like you just plug in these small pieces of details and you're off to the races. And so literally to say I got to this point just before this stream. I literally did get to this setting up of the new participant. Like I said, if you could look at the node repository, you'd see the number of files that are still read because they're using the old types and haven't had these plugged in yet. And obviously, global's been getting plugged in shortly before this stream. And so that's basically where we sit right now. Like I said, this wasn't going to be a super long stream today. This is just covering the state of the progress. I do want to double check some stuff real quick because I do remember last time I missed a message because of how freaking buggy all of these like different ways of trying to actually read messages goes. So let me check real quick. Okay, here we go. And here. Okay, cool. So, all right, cool. So I got a couple questions I want to run by real quick. First, I've gotten this a lot, and I really don't want to like give too much time on it, but I feel like it needs to be said because obviously market conditions being what they are gets people anxious, and frankly, there's more people out there that are willing to be trolls and troublemakers than there are people who want to be bright shining lights in the world. So I just want to remind people. I'm not even going to bother reading the direct question, but it's never as good as it seems, and it's never as bad as it seems. But I would like to remind people that it's worth taking stock in who's willing to say things with a public face and name versus what people are saying behind a pseudonym because they know what they're saying is bullshit. Just something to think about, because it gets very tiring when I hear just people who are regurgitating crap that some rando said to them, and they are just like, is this true? No, just like disregard it, because if somebody was actually saying anything of value, then they would actually bring it up. They wouldn't just say it offhandedly in effectively the digital equivalent of a dark room in hushed whispers. Okay. The next thing was from Otter. And hey, Otter, I absolutely love everything that you write. Honestly, like you've been such a wonderful member of the community, and I absolutely love you so much. You wanted to know what the experience was like building on Quill itself. I wasn't fully going to dive into that this stream, but I will at least tell you like how you get started on that. Just because like obviously this has been kind of backwards order with how we've been trying to get this release out, but high level, it depends on what you're trying to deploy. I imagine for you, because I know you know what you're doing, and you don't care too much about like issuing a token, but it does break down into one of three intrinsics. There's a token intrinsic, which is a customizable, and you can look at the configuration of a token intrinsic in the token configuration Go file, and you can see all the levers that are associated with it. Then there's the hypergraph, which is just a very simple write-read key value store for vertices and hyperedges. This is primarily in the case that you are dealing with like strictly relational structured content that you just need a good storage engine for and a good query engine for that maintains privacy. But the majority of what you're probably most interested in is the compute side. And so where this is relevant for people who are building on Q, for building applications that actually are taking place on the network as a multi-party computation-based app, you would be most interested in the compute intrinsic, and specifically the operations for there we go. Okay. For one, deploying code, and that's not the same as deploying the intrinsic itself, but deploying code, issuing an execution order for that code, and then the finalization of it. These are very simple interfaces. You're essentially just writing data to that particular shard. The actual execution is scheduled upstream between the initiator of the transaction and some random peer of that particular shard that's cooperating with you. How that gets essentially delineated is that you're writing code and it's written in QCL, which is basically Golang. And then you issue so in this case, New code deployment, you set the domain for the deployed shard that you're going to be deploying to. Your source code is just going to be a raw byte string. It's literally just the string of QCL code. When you're issuing proof to it, and you'll be doing this through QClient, by the way, when you issue proof to it, it's calling the compiler to actually compile this, and it puts an output circuit. What's really important to know about this circuit is actually a very standardized format. It's called the Bristol Standard. I hate that name, but that's what it's called. And that standardized format is actually compatible with a lot more than just QCL. There's essentially tooling for LLVM that lets you use practically any language you want. As long as you're targeting the Bristol Standard format, you'll be able to deploy that as a circuit. So this proof step, that's what QClient's calling into. For a like custom implementer that's wanting to do something crazy, you can actually just create the payload yourself instead of calling proof, because it's in the code deployment type. The circuit is that serialized Bristol format. And so you can just plug those values in. That's what proof is doing for you. And that's what you can send in part of that transaction. Execute's just scheduling and picking a rendezvous address to go over the onion router. And then finalize is what gets written to afterwards when everything has settled state. And that's even if it has settled state. So if you want to actually test and evaluate that, the thing you would be interested in is outside of the node package itself. Let me hop back over here because I believe, yeah, it's easier to get to it that way. There is the Bedlam package, which has a standalone compiler that you can use. It has tools for testing locally between two parties. There's also a three-party mode, but it's not ready to go. I wouldn't recommend it. And you can also dive into like the specific work in the compiler side to produce that Bristol format. So if you want to like basically build an application and test out how it runs before it's deployed to the network, that's the package you would want to look at. And the applications that exist within it are what you'll want to use in order to do that testing. Let me see what else. Somebody asked, you don't use OBS? I mean, kind of. Streamlabs is OBS. It's a wrapper for it, but yeah, Streamlabs is kind of bonkers. Okay. Cool. So yeah, I'll stick around for a few more seconds, see if anybody has any additional questions. But yeah, that's basically what today's stream was going to be about, is talking about the consensus engine that we swapped out, the lifecycle management that's being embedded across the entire node implementation, and the upcoming 2105 release. Oh, man, I'm so glad I actually had notifications turned on for that. I wouldn't have seen that otherwise. How can atomic swaps be implemented in Quill? So that would actually be a combination of things. You would be doing a, obviously you would have to have a corresponding token, either like a Quill token, or like if you're doing two different types of tokens, or you would have, if it's just an atomic swap for two tokens of the same kind for whatever reason, you could do that too. But you'd basically have a combination of intrinsic calls for the tokens themselves, and then you would also have the corresponding QCL code that would have that two-party interaction. I do plan on going into more detail on how to actually build that out. That will be, judging from how we'll get 2105 out, that will probably be next Sunday. But yeah, I mean, that's basically the idea, is you'd structure this out in terms of initiating the atomic swap itself, writing it in QCL, which ultimately dispatches to calls on the token intrinsics. Do the future JS SDKs just call Go code like a second layer? It depends. We actually have, if you look in the, where are we? crates. If you look in the crates folder, you'll see that, sorry, losing my voice. If you look in the crates folder, you'll see we have a BLS WASM, Bulletproof WASM, Channel WASM, and Varank WASM. Those 4 libraries are useful for direct interactions with some of the intrinsics on the network. But those are WASM implementations that you can actually delegate into JS calls. So you wouldn't need to call Go code at all. You would just be using JS wrappers of WebAssembly implementations of those libraries. Asking out of interest, could a decentralized permissionless casino exist on the Quill network? Okay. I would say yes, in theory. I mean, it's a permissionless network. If somebody builds something, then it exists. If you were to do that, I would recommend very strongly that you get a lawyer and find out how to legally do this. Because it's obviously tricky. There's different regulations in different countries, and then you'll run into all sorts of fun problems when you get into the international realm, as groups like Megapot are finding out. So get a lawyer if you want to do it, but yeah. All right, let me check anything else. Okay, and cool. All right. Well, that wraps everything up for this session then. So, as always, if you have any questions, I'm available on a whole bunch of different social channels. You can message the Quillink account on X. You can message me at Cass _on_ Mars. Also on X, or at Cassie on Farcaster. I'm also on Telegram, and Discord has a lot of people know and take advantage of regularly. I'm very accessible, so wherever you are, I'm probably there too. So just reach out if you have any questions. Always happy to help. And if you want to contribute to the code base, you can find us at github.com/quilibriumnetwork/monorepo. All right, I think that covers everything for this session. I will see you all probably in a day or two as we get to the tail end of the enrollment process. All right, thanks everybody. I will catch you in the next one.